Hey everyone, welcome to The Explainer. Today we're diving straight into topic 6.1 neural networks. Now, you know the broader media loves to paint these things as mystical, impenetrable black boxes, right? But we know better. Today we're totally stripping away the buzzwords to look at the actual architecture beneath all the hype. Spoiler alert, it's literally just math, not magic.
All right, let's just jump right in. We need to immediately tackle the absolute biggest sci-fi myth out there, the idea that neural networks are somehow these literal, thinking, artificial brains. To see why this is a massive misconception, we actually have to look way back to 1959. That's when Arthur Samuel, an American pioneer over at IBM, coined the term machine learning. Now, why did he use the word learning? I mean, were computers suddenly studying for exams? No, not at all. It was actually just a stroke of pure marketing genius. Kind of like how IBM later pushed the term cognitive computing to stand out. They used machine learning back in the 60s to attract clients and, snap up top talent. The word learning is used strictly as an analogy to animals. It's not literal. Machines absolutely do not learn the way you or I do.
Actually, I want to ground us in reality for a second with this fantastic quote from statistician George Box. All models are wrong, but some are useful. This just brilliantly hits the nail on the head for what we're talking about today. See, what a typical learning machine is actually doing is just finding a mathematical formula. That's the whole shebang. It takes a collection of inputs, our training data, and applies a math formula to spit out desired outputs. If that formula happens to work for most other similar inputs, boom, we call it a useful model. But if you distort those inputs even slightly, the output is probably going to be completely wrong. So again, it's entirely mathematical, not cognitive.
So, here's our roadmap for today. 1. Math instead of magic. 2. The nested function concept. 3. Inside a single unit. 4. The multi-layer perceptron. And finally, 5. The power of nonlinearity.
All right, Section 1, Math instead of Magic, the true nature of machine learning.
Moving on to Section 2, the nested function concept, peeling the first layer.
Now, if you understand basic logistic regression, you've already got the building blocks to understand neural networks. When we really look at the architecture for topic 6.1, a super fascinating truth emerges. A standard unit in a neural network is essentially just a logistic regression model, or, its generalization for multi-class classification. A neural network is simply a mathematical function, exactly like a standard regression model, but it has a very specific flavor. It's a nested function. Think about a 3-layer neural network that returns a single scalar number. The math is literally just y equals f sub 3 of f sub 2 of f sub 1 of x. The output of the very first function just naturally becomes the input for the second, and so on. It's basically a giant assembly line of mathematical formulas.
Which brings us to Section 3, inside a single unit, the core mechanism. Let's zoom in and see exactly how this builds.
Okay, the exact algebra of a single neural network layer is actually elegantly simple. The function for any given layer, let's just call it layer L, looks like this. F sub L of z equals g sub L, applied to the result of w sub L times z plus b sub L. Let's break those variables down a bit so we don't get lost in the alphabet soup. W sub L is our weight matrix. We're using a matrix here instead of a simple vector because the output of the layer is actually a vector function itself. Then b sub L is the bias vector. Now these parameters, the weights and the biases, these are the exact dials the machine is constantly tweaking and optimizing using gradient descent. And finally, g sub L is the activation function. This is just a fixed mathematical function that the data analyst picks out before the learning even kicks off. So chronologically, what's actually happening inside one of these individual units? Well, it's a super strict 3-step process. First off, all the inputs coming into that unit are joined together to form an input vector. You can kind of think of this as gathering all your raw materials. Second, the unit applies a linear transformation to that exact input vector. That's our w sub L times z plus b sub L step. Literally exactly what a linear regression model does. And then step 3, the unit applies the chosen activation function, that g sub L, to the result of that linear transformation. The final result of that activation function is just a real number, which then turns around and becomes the input for the units in the very next layer.
Section 4, the multi-layer perception, connecting the architecture.
And this brilliantly illustrates what we were just talking about. This specific configuration of a feed-forward neural network is called a multi-layer perception, or sometimes you'll hear it called a vanilla neural network. We can map the math we just went over directly onto this structure. Over on the far left in green, we've got a 2-dimensional feature vector acting as our input. Then we have 2 middle layers, which are often called hidden layers, and each of those has 4 rectangular units. Finally, way over on the right in red, we have 1 output layer with a single unit. Inside every single one of those blue and purple rectangles, that exact three-step mathematical process we just learned is happening all at once.
Now, you probably noticed that massive spider web of intersecting black lines connecting those layers. Let's demystify that real quick. That web of lines represents what we call a fully connected architecture. It literally just means that all the outputs of one layer are connected to each and every input of the succeeding layer. And since this is a feed-forward network, the information only ever flows in one single direction, forward, straight from the input layer, through the hidden layers, right out to the output layer.
Section 5. The power of nonlinearity. Why activation functions matter.
Okay, so we've established the math and mapped out the architecture, but there's one massive question still hanging in the air. Why do we even need that G sub L activation function we saw back in step 3? So the crucial point is this. Without those nonlinear activation functions, a neural network would be completely useless for complex problems. The data analyst is completely free to choose any differentiable mathematical function for the activation function. But the whole reason we have these nonlinear components is to let the neural network approximate nonlinear functions out in the real world. Think about it mathematically for a second. A linear function of a linear function is, well, it's still just a linear function. Without nonlinearities, it doesn't matter if you stack hundreds or thousands of layers on top of each other. Your entire massive network would just mathematically collapse down into the equivalent of a basic, flat linear model. So that nonlinear activation function, that is the absolute secret sauce that gives deep learning its incredible power.
And that brings us to a pretty fascinating thought to leave you with today. We've completely stripped away the magic here. We know for a fact that a neural network is really just nested math. Weights, SPI-Cs, and nonlinear activation functions, all methodically finding a formula to map inputs to outputs. But knowing that, just imagine the possibilities. If all it takes is scaling up this highly structured map to handle incredibly complex datasets, what kind of insanely complex real-world logic can we approximate simply by adding more and more of these nonlinear layers? I mean, from translating human languages in real time to recognizing faces, it is literally all just nested math, waiting to be solved. Thanks so much for joining me on this explainer, and keep exploring the math behind the magic.